third circulation changing factor is the torque due to pressure forces. Incidentally, if the fluid is incompressible, this term is zero, and so it cannot change the circulation. To think about this physically, let this be a small fluid particle, and let these be the lines of constant pressure in its neighborhood. The pressure forces acting parallel to these lines exactly cancel each other, and so the net pressure force must be perpendicular, passing through the geometric center. Now let these be the lines of constant density in the fluid particle. If the density lines are parallel to the pressure lines, we call this a barotropic situation, the center of gravity of the fluid particle must lie on the line of the pressure force, so the pressure force produces no torque about the center of gravity. But now suppose that these lines are tilted. So, then the center of gravity of the particle lies on this diameter, and if the density is variable, the center of gravity will no longer lie on the line of the net pressure force, so that this force may produce a torque about the center of gravity, and in that way change the circulation. In a fluid at rest, the lines of constant pressure are horizontal. Since the circulation is forever zero, the lines of constant density must coincide with the lines of constant pressure. That is why the interface and the free surface are also horizontal. If we tilt the interface, it does not remain tilted, as it does in this photographic illusion. The constant pressure lines and constant density lines are now misaligned, and the pressure forces in Kelvin's theorem create a circulation which rectifies the situation. The circulations in natural convection systems are driven by the pressure forces in Kelvin's theorem. One example is the hot water heating system of a house. Another is the principal circulation of the Earth's atmosphere between the cold regions at the poles and the hot regions at the equator. Kelvin's theorem also shows us how irrotational flows may arise. Suppose that you have a motion which begins from rest. If there's no motion, there's no vorticity, and if there's no vorticity, there's no circulation. Suppose, too, that the fluid is barotropic, and that the body forces are conservative, and that viscous forces are negligible. Then the circulation will forever remain zero, and so the vorticity will forever remain zero. The resulting flow is therefore irrotational. Suppose, for example, that an airfoil begins at rest and moves through the fluid. The circulation on all fluid elements is zero to begin with and remains zero, so that the flow remains irrotational everywhere, except in the thin viscous boundary layers where vorticity is produced by viscosity. It is a curious fact that viscosity helps generate lift on an airfoil. Here is an airfoil at rest, with no circulation anywhere. When it begins to move, viscous effects near the trailing edge result in the shedding of a vortex, and thus to a circulation on this curve. But the fluid along this larger curve has not experienced viscous forces, and Kelvin's theorem tells us that the circulation on this curve must be zero. This requires, though, that there be along this other curve surrounding the airfoil a circulation equal and opposite to that on the curve surrounding the vortex. This circulation around the airfoil, which may be ascribed to a fictitious vortex bound in the airfoil, is necessary for the production of lift. Now, when the airfoil stops, the bound vortex is shed as a stopping vortex, again because of viscous forces at the sharp trailing edge. On a circuit around either vortex, viscosity has acted and circulation is present. But on a circuit enclosing both vortices and passing through fluid on which friction has never acted, the circulation remains zero. Thus, the equal and opposite vortices produce zero net flux of vorticity through the entire bounded area. When all the torque-producing factors in Kelvin's theorem are absent, fluid dynamics can be given a beautiful geometrical interpretation in terms of Helmholtz's vortex laws. First, vortex lines never end. They formed closed loops, and the circulation is the same along the length of the loop. Second, a fluid line which at one instant of time is a vortex line will forever after remain a vortex line. Third, on a vortex line of fixed identity, the ratio of the vorticity to the fluid density and the length of the line remains constant as time proceeds. We can illustrate these laws by some experiments. Here are two vortices of equal and opposite strength. They move downwards together. The induced velocity of A moves downward the fluid at B, and vice versa. Each vortex core is convected with the fluid to which it is frozen. Smoke rings also illustrate the vortex laws. You've never seen a smoke ring which is broken somewhere, nor will you ever see one, because vortex lines can never end. The fact that the smoke ring propels itself shows that the vorticity is locked in the fluid, for each element of fluid is propelled forward by the induced velocity of all the other elements of the vortex, and so the whole vortex is convected by itself. The smoke, which after all marks the fluid, is carried with the vortex, again showing that the vorticity is frozen in the fluid. So, as you see, old vortices never die. They only fade away through viscosity. As a vortex ring approaches the wall, it spreads out and slows down. This may be explained in terms of the induced velocity field of the fictitious image vortex on the other side of the wall, which in effect takes the place of the wall itself. This sketch shows the vortex system for a wing of finite span. The circulation that is required for producing lift is created by a vortex bound in the wing. But this bound vortex cannot simply end at the wingtips. The vortex loop is closed by trailing vortices and a starting vortex which is left at the airport. We can make the trailing vortices visible in this apparatus. The camera looks upstream at the trailing edge of the wing. Behind the wing is placed a fine wire grid on which are mounted wool tufts. These wool tufts line themselves up with the flow. The angle of attack of the wing is being increased, and the tip vortices grow in strength as the lift, the circulation, and the strength of the bound vortex also increase. This little vorticity meter shows streamwise vorticity if it is aligned with the flow. It is not a propeller because it turns only if the flow is spinning. If we put it behind a wing, right behind the tip it spins fast. Slightly inboard or outboard, it hardly turns. The trailing vortex is strongly concentrated at the wing tip. The concentration of the trailing vorticity in strong tip vortices results in very low pressures in the centers of these vortices. When this occurs strongly enough in marine propellers, the water in the vortex cores boils and makes the trailing vortices from the blades easily visible. Looking at the induced velocity field of the vortex loop, you can see that there are downwash velocities within the enclosed region. These downwash velocities, which you can see in the tuft pattern behind the wing, act at the wing itself. They make the wing appear to be flying through air which is itself descending, and this results in what is called induced drag. The work of the forward-moving wing, as it moves against this induced drag force, accounts for the kinetic energy being stored in the constantly lengthening trailing vortices. Have you ever wondered why migrating birds fly in formation? One explanation, a plausible one, is that each bird takes best advantage of the upwash velocities in the trailing vortex systems of the ones forward of it. So each bird behind the leader flies on an ascending air current. You should keep in mind that the vortex laws come from the ordinary dynamical equations of motion. So anything you learn from the vortex laws can also be found by thinking about the pressure field. With the lifting wing, for example, air can leak around the tip from the high pressure region to the low pressure region. This leakage produces a transverse flow which accounts for the tip vortex. To show the effect of stretching vortex lines, we have an apparatus in which water flows over a hump. The water depth first decreases and then increases. The speed of the water is inversely proportional to the depth, and so the flow accelerates as it goes up the hump and then decelerates as it goes down the hump. Now I'm making a vortex with a sharp-edged plate. This vortex has its axis vertical. As it goes up the hump, the length of the vertical vortex line decreases, and so the vorticity decreases, as you can see by the spin. When the vortex line goes down the hump, the length of the line increases, and the rate of spin also increases. The effect going down the hump, however, is not as strong as the effect going up the hump. That is because viscosity is always acting to decrease the rate of spin of the ping-pong ball. When a vertical thread of fluid moves up the hump, its length decreases, but the volume of the thread remains the same, and so its diameter must increase. This also increases the radius of gyration. To conserve the moment of momentum, the rate of spin must decrease. Now, when the vertical thread of fluid goes down the hump, it stretches and becomes thinner. Therefore, the rate of spin must now increase. A figure skater does the same thing. She speeds up by decreasing her moment of inertia. Turbulent flows are full of vorticity. The vortex lines are like tangled spaghetti. The mutually induced velocities of these vortex lines causes some of them to lengthen, and this lengthening produces a finer grained turbulence with higher velocity gradients. This makes for added viscous dissipation. Big whirls make little whirls, which feed on their velocity. Little whirls make lesser whirls, and so on to viscosity. In this open channel, water flows around a bend. Upstream, the flow is parallel to the walls of the channel. Because of the boundary layer on the bottom of the channel, the upstream flow has a horizontal component of vorticity in a direction transverse to the flow. But upstream, there is no vorticity component in the vertical direction, nor in the streamwise direction. Now I am putting in the little streamwise vorticity meter at the end of the bend. Somehow, a streamwise component of vorticity has been generated in the bend. To see why, let's look at three perpendicular fluid lines, A, B, and C, in the upstream position. If we neglect viscous forces compared with inertial forces in the bend, we may imagine the vortex lines to be frozen to these three fluid lines. Notice, though, that there is no vertical component of vorticity C nor any streamwise component of vorticity B. There is only a transverse component of vorticity A, associated with the viscous boundary layer on the floor of the channel. Now line C moves along the center stream line to position C prime, so there is no vertical component of vorticity, C prime. The vertical component of vorticity is connected with the turning of the lines A and B. Line B follows its streamline and therefore rotates in a counterclockwise sense. Since the vertical vorticity remains zero, line A must rotate clockwise by an equal amount. This clockwise turning of line A into position A prime requires that the velocity at the inside of the bend be greater than the velocity at the outside. The important point is that the vortex line A prime now has two components. One component transverse to the flow, which we had before, and a new component along the flow, which we did not have before. This new component, which is called the secondary vorticity, is what causes the water at the surface to move from the inside toward the outside of the bend. And these heavy oil droplets, which move along the floor, show that the flow on the bottom moves toward the inside of the bend. Such secondary flows often occur when a channel is curved. When a river goes round a bend, the secondary flow erodes the outer bank and deposits sand and pebbles on the inner bank. This tends to make the bend get more bendy. Some people think that this is one of the mechanisms by which exaggerated cases of meandering occur. When a pipe is curved, there are two cells of secondary flow. These secondary flows carry high-energy fluid from the middle of the pipe to the walls, in this way increasing the frictional losses. The vortex laws are also illustrated by the flow in this long channel as it goes under a circular cylinder. Strong vortices are developed from the vorticity present in the viscous boundary layers on the two side walls. Suppose that this thread of fluid coincides with one of the vertical vortex lines. As it moves downstream, it is both bent and stretched. The stretching of the vortex line intensifies the vorticity and makes the vortex core visible. The bending of the line produces a streamwise component of vorticity because the vorticity is locked in the fluid. I'm going to make some vertical vorticity in this jar. Now, out with the plug. See how quickly the strong vortex forms. This thread of fluid is also a vortex line. When the flow begins, the thread is enormously lengthened, and the vorticity increases proportionately. A similar mechanism underlies the formation of tornadoes. You can see the vortex core of this tornado by the dust in the updraft. Notice also the air flowing inwards and feeding the vortex. The centrifugal pressure field of the vortex creates such a very low pressure at its center that houses over which the eye of the tornado passes literally explode. Watch the house in the lower left-hand corner. In our large tank, before we started the flow, The fluid had a very small vorticity in inertial space due to the turning of the Earth. When the plug was pulled, the vertical fluid thread on the axis was enormously lengthened, and the vorticity in inertial space was strengthened proportionately, finally to the point where we could see it in the reference frame of the Earth. These photographs of the Earth's cloud cover, taken from the satellite Tyros, show that similar events occur in the Earth's atmosphere on a grand scale.